Hi, I'm Jay Phelan. Let's learn some biology. When we're trying to understand genetics, the inheritance of traits, why offspring resemble their parents more than they resemble some other individual in the population, one of the most useful tools that we have is the pedigree. So today we're going to look at that tool and work through a couple of examples to show how it can guide us to figure out what is going on at the genotype level when all we can see is the phenotype level. People are fascinated and kind of obsessed with pedigrees in many different domains. People who are thinking about buying a dog or they're dog breeders, if you can say this is pedigreed, or if you can demonstrate the pedigree, that is the family history. Who are the parents, who are the grandparents, who are the great-grandparents, and so on. People like that. So they have, outside of genetics, academic genetics, people have been working on this for a long, long time. You can go online if you're interested in horses, and you can buy these reports and so on. Humans as well, just in our own world, are interested in questions that can be addressed with the help of pedigrees. So what's the probability that I'm going to have a child that has this trait? What's the probability that I'm going to develop this trait at some point in my life? If we have X number of children, what percentage of them can we expect to have a trait or not have a trait, and so on. So the issue of why we value these pedigrees so much is that if you have enough information, you can start to figure out, you can deduce what the genotypes are without actually having some sort of sequence analysis that would tell you what allele an individual carries. A pedigree is going to look like this. It will have squares that represent males, it'll have circles that represent females, and they will be organized on the pedigree with a line connecting individuals that produce offspring, and then coming down from them, all of the offspring in a particular generation. So if you look at horizontal rows, you'll see generation 1, generation 2, generation 3, and so on. Obviously, they keep going back, so it's not like you can have ever a complete thing. You're just looking in at a snapshot of something. They're also going to either be filled in, meaning that an individual exhibits a trait. Maybe it's a genetic disease, some kind of disorder. Maybe it's just some physical characteristic. Or they'll be not filled in, and that means that they don't exhibit the trait. By looking at that, we can then figure some stuff out. So for instance, here is a pedigree, just 3 generations worth, that gives us the inheritance pattern that we've seen for retinitis pigmentosa. And this is a condition, a human condition that causes the lack of, a loss of night vision. And we want to know, how is the trait inherited? And by that I mean, is it dominant or is it recessive? Is it autosomal or is it sex-linked? And we can rule out certain possibilities. Here's what's going on. You get this progressive deterioration of the rods, and what happens is that an individual who has this progressively will have what is kind of a tunnel vision. Here's another one. And so as it progresses, the vision gets worse and worse and worse. So this pedigree here has been collected by looking at individuals. We see here 1, 2, 3, 4, 5 individuals on this pedigree show the trait retinitis pigmentosa, and we're trying to understand what's the mode of inheritance. First question we'd ask, typically I like to ask this first, is could it be a dominant trait? The reason I like to ask this is that it's fairly easy to rule it out if that's not the case. In this one, we'd say, all right, if it's a dominant trait, any individual showing the trait has to have an allele for that trait. So you look here, and we've got this individual here. It's a male in the 3rd generation. Has to have one of the alleles, dominant trait. But if it has the allele, where did it get the allele from? Had to get it from its mother or father. But if its mother or father had a dominant allele, they'd show the trait. And yet both of them are white, so they don't have the trait. Therefore, there's an internal contradiction if it were passed on as a dominant trait. So we get to rule that out. And it means back to the drawing board. Let's try another one of our 4 options. Actually, in this case, we can rule out sex-linked dominant and autosomal dominant. So now we're narrowed down to 2 options. Could it be sex-linked? Well, how do we do this? There are rules people will tell you, oh, if a male shows it, then you'd have only females, or I can't even remember. I find it easier to use trial and error. Just figure it out. Try to fill in as many of the genotypes as you can. So if we want to examine, is this a sex-linked recessive? The top left individual is a female, so we would put 2 X's as our placeholders. The sex-linked trait is going to be on the X chromosome, and we're saying that it's recessive. Since she shows the trait, we have to put 2 little b's. That has to be her genotype if this were the case. Then we can start filling in other individuals. So for instance, this male, first we put in X and a Y, so we remember that he only has 1 copy of the allele. He doesn't show the trait, so it has to be a capital B, the dominant allele. Now we follow through. So far so good. Seems like it could be this. We look down at this daughter that they have. Well, she's a daughter, so she has 2 X's, which means she gets an X from her mother. That has to be X with a little b. That's all the mother has to give. From the father, X with a big B. That's all he has to give. Therefore, she has one of the dominant alleles. If it's a sex-linked recessive, that means she's not going to show the trait. So far, so good. We move on. You look elsewhere. Now, I see this male over here. He's a male, so X and Y. Has to get the Y from his father. So he has to get the X from his mother. Well, what does she give? X with a little b. Sex-linked recessive trait, he'd show it. He's filled in. Yeah, that's consistent too. Let's move one over, and we look at this female. 2 X's, she's a female, so she gets 1 X from her mother. That's going to be an X with a little b. That's all the mother has to give. From her father, she has to get an X with a big B. That's all he has. But if she got an X with a big B, then she can't show a recessive trait because the dominant trait is going to mask it. So that doesn't work. You'd look at it and you'd think, all right, well, no, it doesn't work, does not compute. So since we know that these observations we've made aren't consistent with sex-linked recessive, we have to rule that out. So you try again. Well, we've ruled out dominant traits and we've ruled out sex-linked recessive. So now we'd look at autosomal recessive, assuming that this is going to work out. If that's the case, this female has to show it, so she's little b. The male here that shows it, also little b. Everybody who has it has to be little b. Now we start filling in the individuals who don't show the trait. This one, he has to have 1 big B. But maybe he's homozygous dominant, maybe he's heterozygous. We don't know. But we just leave it there. We haven't contradicted anything. We look down here, this new individual in the second generation on the far right. She doesn't show the trait, so she has to have a big B. We don't know what the other one is. Go through, you can fill in all these different individuals. If they don't show the trait, they have to have a big B. Make sure that they have a parent that they could get it from. From the other parent, then, what do we know? Well, this individual here, the first male, he has to have a little b because he's produced offspring. His wife here, she's little b. When they produce a kid that shows this autosomal recessive, that individual has to get the little b from both parents. So we know the father now. We've been able to fill in that he's not homozygous dominant, he's heterozygous. And that works with a bunch of the individuals in the pedigree. You look and you think, all right, could that work out? Now, in the third generation, for instance, I see here's an individual that has it, little b. So you'd say, well, that male has to get from each of its parents. That can work out. So you do this, and one by one you go through and you fill in as many genotypes as you can. And if nothing gets contradicted, where an individual, based on what we observe, has to have a genotype, but their parents don't have the proper alleles to give them, then you rule it out. So in this case, we could say, could be autosomal dominant. You want to be careful not to say it is. It's just consistent with this. We only have 3 generations. We have a limited number of individuals. We use certain conventions when we are presenting a pedigree or analyzing one. And one important one is you'll hear people refer to as a carrier. And a carrier refers to an individual who has a recessive allele for a particular trait or disorder and does not show the trait or doesn't show symptoms of it. So we'd call them a carrier, meaning that they might be able to pass it on. We don't see it in them, but depending on who else is contributing alleles to their offspring, they might be able to pass it on. You have to assume when we do these that no errors in observation have occurred. And that should go without saying, except remember, we're looking at multiple generations. If we're talking about mice or fruit flies, okay, that might be the course of a few months or a few years. But if we're looking at humans and we're going back 4, 5, 6 generations, that's a long time. So you don't know the people who collected the data. We assume that no errors in observation have been made. We assume that the parentage is as put forth in the pedigree. So we don't assume, oh, maybe, because we have some paternity uncertainty, maybe that's not really the father. We assume that the individual is. You also assume that no mutations have occurred. People love to do that when they can't figure it out. Well, maybe a mutation occurred. That's why we see the trait. Mutations are so rare, it's never the answer. So if you think you want to write it down as the answer, figuring out a pedigree, don't. You're wrong. So we assume that that's not the case just because they're so rare. And as I said previously, we rule things out. That's what we can do with certainty. We can rule out a mode of inheritance, but we don't necessarily say, yes, this is it. We say, it's consistent with all the information we have. That's why you might want to look at additional individuals, additional generations. For some human traits, people will have thousands of individuals that they'll be looking at. And the reason for this is that not all traits are just autosomal or sex-linked, dominant or recessive. And in other videos, we're going to talk about all the different ways that going from a genotype to a phenotype can be complex: codominance, incomplete dominance, environmental effects, and so on. So things are not always as simple and straightforward as we imagine. You might get a question like this. After we've determined that in this pedigree that it's consistent with autosomal recessive, then we'd say, all right, if individual 3-4, that means third generation, fourth individual over. So that's a female. If she and the male, third generation, fifth individual over, had a child, what's the probability that it has retinitis pigmentosa? Then you'd have to figure that out. What's the probability that they have a little b? And then what's the probability that they pass that on to their offspring? So Mendel's law of segregation will be relevant there, and the observation of what it is also going to be relevant there. Let's look at another example. Here is a condition. It's called anury, and it is the case of dogs that are born without having a tail. It's inherited as a recessive trait. It's an autosomal recessive trait. Here's a little pedigree. So we've only got about, 6 individuals, almost 6 individuals here. But I want to look at it to introduce the idea of incorporating probabilities into pedigrees. And we're going to talk a lot more about those in another video. So in this case, we look at individual 3. It's a male, and it's filled in, meaning that it has anury. Neither the parents does. So we want to know now, what are the genotypes of these individuals? We can say for individual 3, it's got to be, depending on what letter we put in, little b. It's got 2 copies of the recessive, homozygous recessive. For each of the parents, they don't show the trait. They're not exhibiting anury. They have to have at least 1 dominant allele. But we know more than that. They had an offspring that is homozygous recessive. Therefore, even though we first put the big B because their phenotype says, I'm not homozygous recessive, we can also say that they're both carriers. They pass it on to individual 3, and that's what we get. Now we've got this dotted line around a male here, so it's a puppy, and we don't have that much information about it. What we're trying to figure out is what's the probability that this individual is going to have anury? Well, we see that the father is filled in, so we know his genotype has to be little b. The way we solve this one is we know that the new puppy here has to have a little b because that's all the father has to give. But from the mother, let's figure out what we know. The probability that this unknown puppy is going to have anury is going to be the probability that the mother is heterozygous because the mother has to have an allele that it can pass on, the little b, and the probability that she passes it on, Mendel's law of segregation. That's going to be 50%. So we look at this and we say, all right, it's going to be some probability that she is heterozygous times half. Now we look and we think, all right, well, what's the probability that she is heterozygous? Well, her parents were both heterozygous. So you might think, I know from the Punnett square, if I cross 2 individuals that are heterozygous for a trait, that I have 1/4 are homozygous dominant, 1/4 are homozygous recessive, and half are heterozygous. But don't be tempted to put in half, like, that's the probability that she's heterozygous. That would be the probability if we knew nothing about her, but we know something about her, right? We look at her, not filled in. She doesn't have anury. So out of those 4 options, when you cross 2 heterozygotes in the Punnett square, we can get rid of the one that says you have anury. So there are actually only 3 options. And of those 3 options, how many of them are heterozygous? 2 of them. So 2 out of the 3 are heterozygous. So you say, all right, so the probability that she's heterozygous, 2/3. Mendel's law of segregation. What's the probability then, if she is heterozygous, that she passes 1 on? Because both of those things have to happen. That's half. So 2/3 times 1/2 is 1/3. We can say that's the probability that that puppy is born with anury. So our take-home message here is that whether you're a scientist, a doctor, a plant breeder, animal breeder, or you're a parent thinking about kids that you're going to have, that pedigrees help us to figure out the likelihood that any given offspring or any individual, based on their parent and their siblings and their offspring, the probability that they are going to exhibit a particular trait. So there we have it. There's a lot we can learn about genetics by interpreting pedigrees.